Welcome all to the study guide review. So today we're going to be going over the study guide for your Unit 1 test, and I'm going to be asking for some responses. So please help me out as we go through this. I'll be actually filling some of this out. Some of it we'll just talk about. Anything that's got numbers, I'm going to try to fill out. Anything that's got words, not a guarantee. But the first one we're going to go over is talking about the scientific method. So the scientific method seems to be this big deal in science, and there's supposedly 7 steps. So do you guys remember them? What are those 7 steps? Anybody? What's the first thing you do in science?
You form a hypothesis.
All right, so there's actually a point that happens before that, and it's going to be forming a question, which is similar, but it's a little bit less informed. So the first thing you do is you notice something that raises a question. All right, so we're going to notice something that raises a question, and that lets us know to start investigating. All right, now what's after that? Now that you've got a question,
Research.
yeah, you're going to actually research. So here, you're going to go through and you're going to put some research down on the page so that you now know what to do with that question, because the question might not be meaningful at first. And you want to try to find a way to form an experiment and to look for a relationship that might be meaningful. And in order to do so, you're going to research. So you're going to do some research and get some information about this question. Now, what comes after that research?
Then you have the hypothesis.
There we go. Now we've got our hypothesis. So you've noticed something, you've asked a question, and then now that you've actually done some research, you know how to form a question that then becomes an experiment. You want to base your experiment off of that hypothesis. So you want to make sure it's worded and structured correctly. So you're going to set it up generally as an if-then statement, and it's going to allow you to say, if I do this or if I change this, then I expect the result to change in some expected way. All right, so we've got 3 out of 7, so we're moving along pretty nicely. You guys are pulling them out. All right, so what do you do after you form that hypothesis? Now that you know what you'd like to test, what are you going to do?
Experiment.
You're actually going to start carrying out that experiment. So here you're going to do your experiment. All right, now as you do this experiment, you're going to follow along what the research suggested the relationship might be, and that hypothesis you stated. You made a claim. You're going to say, I think this will happen, and I'm going to set up my experiment in order to determine that. So you go through the experiment, which generally means determining procedures in order to test that hypothesis, collecting materials that are going to allow you to do that procedure, and then writing everything down. All right, so this is a huge key part of the experimental design and the experimental implementation is actually writing down what happens, because something might happen unexpectedly. And if that happens, you have to account for that, because otherwise it's going to show up in your data and you might not know why. You might just see a data point that looks anomalous or looks out of the ordinary. And if you didn't write down, right then I sneezed on my culture, that's why this one Petri dish has 1 billion times more bacteria than any other one. If you didn't write that down, whatever you were testing in that one Petri dish would seem like it was causing that change. All right, so you'd want to write something like that down. So now that we've formed a question, we've done some research to inform that question, we've then made a hypothesis and told ourselves we want to test these two things in comparison to each other. Then we set up an experiment, do that experiment, write it all down. Now that we have an experiment, what are we going to do next?
Gather your data.
There we go. So we're going to collect data. All right, so this is what the point of our experiment actually is for numbers or qualitative data, depending, and we'll get into those in just a sec. But you are generally going to collect data in order to try to find that relationship that we were saying might exist in our hypothesis. So you've experimented and part of that experiment, and really you're looking at that. So I'm going to say collect data / analyze. You want to look at it. It's not just collecting it. Oh, look at these numbers. That's real neat. I got these numbers. Now I'm done. You actually have to figure out what those numbers mean and whether they go along with what you thought the case might be. All right, so now you've collected your data, you've done the experiment, all that good stuff. What do you do next?
Write the conclusion.
There we go. So now we're writing our conclusion. So we're going to go back and we're going to try to figure out what happened. Okay, we're going to write down what happened, and then we're going to look back at what we thought would happen, and we're going to say, was I right or was I wrong? And then you're going to have to justify either of those. If you're wrong, you're going to have to say, well, the data shows that there wasn't the relationship that I expected. There might be this other kind of relationship based on the data that I see. So if you're wrong, you're not just going to be like, oh, man, I was wrong, and the data shows I'm wrong. You would say, I'm wrong. The data shows I'm wrong. But I think that the data might actually suggest this trend. In future experiments, I'd like to test these two variables. If you were right, you'd say, well, I was right, and the data seems to suggest that the relationship that I thought existed strongly. Here is the examples in the data, and this suggests that further testing is needed to be done to confirm these results. All right, so now you've made your conclusion, and now what do? Now this is all for you. This is all for your hypothesis. What's that final step in science?
Communicate your results.
Exactly. Now comes the important part, the communication. This is where you open up what you thought happened to others, and you invite them to pick it apart and try to find holes or issues with it. Now that sounds very defeatist, right? I did all this work, I've recorded it, I spent all this time, now tell me I'm wrong. The reason we do this in science is because if you are wrong and no one tells you you're wrong, that could affect millions of people depending on what you're researching. All right, so you want somebody to come through. You want somebody to say, hey, actually, it looks, you said you sneezed here, and this particular sample you were working on might have been contaminated. We might need to run the whole experiment again just to make sure before we go out and we make this new drug or we make this new antibody or something like that. Well, regardless of what you're researching, you always want somebody who wants to prove you wrong to unfortunately prove you right. That's what science is all about. You've got people from around the world who would like to see your research not be correct, actually prove it correct. So if they set out to try to prove you wrong and in the process prove you right, you did it. That looks really solid. All right, so it's going to go through editing. So people are going to make sure you spelled things right because we know you're a scientist and not an English major. And then it's going to go through publication. And publication is going to be like editing, but for the science. You're going to have a panel of scientists who have done research papers and know what published papers look like. Pick it apart with a fine-tooth comb and a scalpel. And they're going to make sure that it's up to par with what they're looking for. All right, so it's a very, very, very important process. So I'm going to make one note here that doesn't go along with the study guide, but it will really help you understand why the communication part is so important. It's because science is an ever-changing body of facts. It's constantly added to. It is never the same from day to day, minute to minute. New things are being discovered. New things are being rediscovered, meaning like more information is being uncovered about it every single day. And that means that our baseline information for science is also always growing. And sometimes that means throwing out old statements and then rewriting them more correctly. And if that's the case, that means that if you're communicating with the public, that sometimes sends mixed messages, especially if the media gets a hold of stuff before it's ready to be communicated, which happens all the time. Lots of media specialists will actually go and scout out things that have not been published. If it's not published science, it's not science, but it's a tabloid headline. So I will warn you that that's a trend that happens pretty often. But let me give you one example of communication changing within the scientific community that directly affected the public, and it affected them in a big way recently. And so that is going to be the mask information that they were putting out at the very beginning of the pandemic. So if you were keeping up with it right about the time we were getting out of school in March, and when most of the country was starting to go on pandemic lockdown, there were multiple messages coming out from the scientific community within the course of about 2 weeks about whether or not to wear masks and whether it would do anything. And initially they said yes, then they took that back and said no, and then they said yes. All right, so initially they said yes before we shut down, before there's an actual pandemic in place, so to speak. And they said yes because it does slow transmission. That's why surgeons wear masks in surgery. It's why doctors and nurses wear masks in a regular year. But when they said yes, people flooded the stores trying to find them. They flooded the online stores trying to buy them online. And so what ended up happening is two things. One thing is that new science came out and suggested that they are not 100% effective. And some scientists communicated that. Some scientists said, look, these aren't 100% effective. If you're wearing it, it's really just going to protect others from you. The whole message of everyone needs to wear one, meaning if both parties wear one, there's a 90% decrease in transmission. That message had not really been pushed yet. The doctors are looking at individuals wearing them and the effectiveness, and that's only about a 30% decrease. And so they were looking at 30% decrease. Yeah, that's helpful, but it's not even halfway. And then they balanced it with the idea that we were running out of masks for medical workers. All right, we weren't running out of masks in general, but the kind of masks that medical workers use on a very large scale, which is the N95s, were flying off the shelves. They were flying off the shelves. The distributors could not keep them stocked, and we ran out. At that point, the scientific community, who's very in touch with the healthcare community, because all healthcare workers are scientists, were immediately panicking, thinking that our doctors and nurses who were being exposed directly to this disease were going to be at huge risk if they didn't have the right masks. And they were finding that individuals wearing them just by themselves only decreased the risk of catching it by 30%. They put these two facts together, gave them to the public, and said, your masks aren't as effective. They're not 100% effective. And the healthcare workers need it more. So you don't need them right now. The healthcare workers need them. The media outlets took this and run with it, and then suddenly say CDC, HOW, suddenly reversing message on mask mandates, that kind of thing, because that sounds really interesting and you want to click on it. And then 2 weeks later, the shortage died down. More research had been done on the effectiveness on masks, and then they took into account that two people wearing masks took it from 30% to almost 90% effectiveness. And then they put out a new statement stating you need to wear masks. But they found that you didn't need to wear the N95s. They were almost too effective for what humans, or for what normal people out on the street needed. Just cloth face coverings would actually do the job to about 70% and work a lot better than absolutely nothing. So things like bandanas or things put over the face. But this was an actively changing body of science. And then people who already had a distrust of science used this example to say, look, the scientists don't know what they're talking about. They're constantly changing their story. And in the court of law, yeah, changing your story looks pretty guilty, right? If, oh, it was this thing and then it's this thing. But if new evidence comes out and your whole story is based upon evidence, of course you're going to change your story. You're trying to update the public as quickly and effectively as possible. So this is just one current recent example of how a changing body of facts changes what scientists communicate. And this is also to tell you that you should not take that as a reason not to trust scientists. All right, so we're going to go ahead and move on. I just want to give you an example of science at work. So we're going to kind of move pretty quickly through here. What is a hypothesis?
Educated guess.
All right, so an educated guess is a real quick, short, sweet answer. So I'm going to ask you to think about it a little bit different and call it a researched prediction. All right, and so that's an educated guess would be that first question you come up with, right? That's just based on what you know in your brain, and you got to guess. Once you've done that research, though, you are researched in this thing, and you're going to make a prediction, because a guess just sounds flimsy. All right, so research prediction. Why is it important, or what is important about the hypothesis?
Because you must be able to create an experiment based on the question.
There we go. The hypothesis takes your random question that popped into your brain and makes it an experiment. This is what you are guiding your experiment with, and it details your independent and your dependent variables. All right, what must your conclusion refer to and do?
It has to restate hypothesis and state whether your data supported or rejected your hypothesis.
Exactly. So it's got to tie back into your data and your hypothesis. So it's your opportunity to say whether you're right or wrong, and then why, by referencing the data that you took during your experiment. So it is a very good way, like generally the two things that any scientist reads for a paper to realize whether they need to read the whole thing, they will read an abstract, which is like a conclusion, but at the very beginning, and they don't give away everything. And then they'll go straight to the conclusion and just read what the conclusion was. And if they want to see the data procedures and all that good stuff, they'll go back and they'll reread. This is if you're reading someone else's published journal, if you're just trying to figure out what the results were. And so the conclusion is a really good summary of everything that happened. Now, why is repeating your experiment more than once or even more than 3 or 4 times so dang important in science?
The more
for
data you
accuracy.
have, the more accurate your experiment will be.
Yes. So the more data you take, the more accurate your results are. So if you've ever played sports, you know you're not going to sink every three-pointer. You're not going to hit a home run every single time. You just won't. It's statistically impossible. You're going to hit a brick sometimes off the rim or something. You're going to hit a pop fly or a foul ball. You're going to make mistakes. And what you want is you want your data to be so robust that it actually accommodates for that mistake. It has so much good data that that one mistake, you know what, it's not that bad. It actually gets averaged out in the end.
What?
Then number 6 is what is an independent variable within an experiment?
The factor you change on purpose.
There we go. So this is the variable you're actively changing and you're manipulating. You are moving that from one end of the spectrum to the other. You're trying to find a way to control this variable and change it. So this is what you are actively changing. Now, if that's what you're changing, what's the dependent variable?
The one you don't change.
So it's the one you don't change, but what does it do?
The result of whatever you changed.
So this is what's going to respond to what you changed. All right, so as you change something, you are going to actively be watching your dependent variable to see how it responds to that change. So the way I like to think about this is that the independent variable is the one you change, and the dependent variable is the one that you measure. All right, so you're going to be measuring some change in that dependent variable as a result of what you did to the independent variable. What is our control group within an experiment?
The group in which you don't change anything.
So exactly, the control group is the one that you are controlling to be normal. It is your baseline or your reference group. This is what you want to compare anything that you changed back to this to see if there is a difference. You have to have a baseline to compare to, and that's what your control group is for. All right, what about constants within an experiment?
Things that remain the same in both experiments so that the experiment can be fair.
There we go. So this is a way to ensure that it is just the variable you're looking at that's making a difference. So you want to keep everything that you're not testing for exactly the same so that you don't accidentally increase the likelihood of seeing a change where there wouldn't be one before. So if we're using the example from the PowerPoints that we looked at, the car with the engine size, you were testing speed versus engine size. You know, if the engine size is bigger, does it get faster? But you wouldn't want to change the tires. You wouldn't want to drive it on a different track. And you'd probably want to make sure that the track was dry every day that you tested it so that you can confidently say it was the engine and nothing else that affected performance. So this is a way to just keep everything fair. All right, so you've got all these kinds of variables and stuff, and then now we're taking data. So what is qualitative data?
It's like the qualities of something.
So yeah, that's a way to think about it. So the qualities of something, how do we describe qualitative data? What do we use?
Words.
Words. So here you're going to use words, not numbers. And it is stuff that you pick up with your 5 senses. So if you can pick them up with your 5 senses, give me 2 examples of qualitative data. What are things that you can sense?
Smell
Mm-hmm.
and texture.
Smell, texture,
It looks healthier.
sound, healthier, right? If it's just using your eyes, you can't measure it with numbers. You're just going to have to describe what you're seeing. Then you're going to be taking qualitative data. All right. So what about quantitative data?
It results that can be measured and described by numbers.
There we go. So quanta or quantitate or quantify, these are all words that mean numbers. So quantitative data is data that actually requires numbers to describe it. So this is something that you're actively going to measure. Given that you're going to measure it with numbers, give me 2 examples of quantitative data.
Growth rate.
Growth rate, so the plant example, awesome. What else?
The speed of something.
There we go. So you guys actually just gave me 2 rates of change, which I love, which would be height per unit time, so how quickly it's growing in a certain amount of time, and then distance per unit time, how quickly it's moving a distance in a certain amount of time. But both of these are compound quantitative data. So you can measure distance, you can measure time, you can put them together and measure the rate of change of distance over time, which is speed. And then you can measure height, you can measure time, and you can put them together and measure the growth rate or the rate of change of growth per unit time. So good examples, good examples. So we will come back to these after we've done this. I just want to get out of the scientific method brain. We just spent, almost 20 minutes talking about it. We'll come right back to it after we finish this bottom slide. or this bottom page, all right? So just bear with me. I just don't want to drone on straight through it. So now we've got metric systems, and I'm just going to remind you that the metric system is the used system of units for most of the world and all of science. So all of the scientific community is going to actively use SI units, which stands for System International, which is because most countries internationally use these systems of measurement. And it's a 10-based system based on the fact that we've got 10 digits, and 10 is really easy to count from. You're just adding or subtracting zeros to a thing and moving decimal points around. So it becomes really easy to convert from one size to another and communicate that size if it's large or small through scientific notation. So let's go ahead and look at one. What are the SI units for the following? What is our SI unit for mass? Remember, this one's a little different.
Kilograms?
There we go, kilogram. Remember, this is the only one that comes along with the prefix. And this is because the unit gram is so small compared to everyday objects. We'd be talking about hundreds or thousands of grams for anything that we measure frequently. So we throw in that kilo just to make it more full. 1 second. He does not need to be here. All right, I gotta let, there we go. So we went away. So we've got kilograms there. Then what's next? What's B? Length.
Meters.
Meters. All right, so this is going to be meters. I'll remind you that's about 3 feet. It's about 39.25 or something like that inches. But meter is going to be the way we measure things pretty frequently in here. And I know, what about volume?
A cubic meter?
All right, so technically a cubic centimeter or a cubic meter, some cubic length distance also is a measurement for volume. But you're going to be referring back to length there. So let's think about the volume measurement that's just volume by itself.
I put liter.
Liter. All right, so the liter is the same thing as a cubic meter. So you are in the right mindset there. But we're going to talk about it as liter because that's the volume only measurement. Like you couldn't describe any of these as some amount of liters. You would only describe volume as liters. All right, and then last but not least, time.
Second.
Second. All right, so this one you should know. You've known for most of your life. It's the way we measure time in general. Why reinvent the wheel or the clock? So we've just got the same time measurement that we use generally. And now number 2, we mentioned this earlier, but which of these SI units, which of these 4, is the only one that involves a prefix?
Mass?
Mass. All right, so what was that unit and the prefix?
Kilograms?
Kilograms. All right, so kilogram is going to be the answer there, and that's again because grams are so small. All right, so let's look at number 3. What are the order of the 7 prefixes you are required to know in order from largest to smallest? So we're going to start over here and end over there. So what's our largest? I'm just going to write the letter.
Deca?
The very largest.
Kilo.
Kilo.
All right, so this one's going to be kilo. So we've got kilo here for 1,000. What comes after kilo?
Hecto.
Hecto. Hecto means 100. Remember, that's a factor of 10. Then we get to this next one.
Deca.
This one is deca. Now I'm going to write this as DA just to signify that there's an A attached. And what comes after deca? If this is 10, what's 1/10 of 10?
Base.
Our base unit. All right, so we're right there at base. Now let's look right here. We're now into the 10th place.
Deci.
Deci. I'm just going to write that as a capital D. All right, and then what's next after deci?
Centi.
Centi, and then last but not least,
Milli.
milli. All right, it is actually the least. That was a joke. So we've got kilo, hecto, deca, base, deci, centi, milli. And again, the ones that we will probably use the most often are going to be, oh, why is that not red? There we go. We're going to be using milli, centi. Of course, we're going to use the base, and then kilo. These are the ones that you will see on your test. So these are the ones you'll need to know how to convert between, all right? So this isn't the test, so we're going to be converting just randomly between them. Let's go ahead and do some of these conversions. I'll do the first two for you, and then I'm going to do the next ones with you, okay? So I'm going to need your help for 3 through 8. So number 1, we've got 8.9 decigrams, and we want to know how many centigrams that is. So we're going to figure out where we're starting, and that's going to be deci, so we're right there. And we're going to centi, so that's just one jump, and we're going to jump to the right, all right? So if we're going from deci to centi, and we're going to move to the right just once, we're going to do the exact same thing with our decimal point. And so we've got 8.9 there, and so we're going to move to the right just one time. And we're going to find this to be 89 centigrams. All right, so we've moved that decimal point just once to 89. All righty. Now we're looking right here at 103.29 milliliters to decaliters. All right, so let's figure out where we're starting. We're starting with milli, which is all the way down here. And we're going to end up all the way over here at deca. So we're going to be moving left. Let's figure out how many times. That's 1, 2, 3, 4 times to the left. Well, if I moved 4 times to the left to get there, I'm going to move my decimal point 4 times to the left. Zoom in a little bit more so I don't, completely come off the screen. So if I move my decimal to the left, that's 1, 2, 3. I'm going to have to add a 0 in front of that 1. So it'll be 0.10329. All right, so that's going to be our answer there. So in the same mindset, let's go ahead and talk about our number 3 right here, which is 0.62 kilometers. All right, who wants to help me out? Anybody?
Since you only have to move the decimal 1 place to the left, you end up having 62 hectometers.
Right, so the answer is correct. You said moving to the left. I'm just going to make a quick note there. We're actually moving to the right. And then your number was 62, which is, like I said, you got the right answer. You flipped your directions there. So she said 62 hectometers. All right, so we're going to write 6.2. We start with kilo, heading to hecto. That's 1 jump to the right. Move that decimal point just once. Good answer. Thank you, thank you. All right. Next up, number 4, 30.28 decameters to decimeters.
Callie, what's wrong? Tell me what's wrong.
Jolie, can I get you to mute yourself for me, please?
Oh, I'm so sorry.
All right, so who would like to answer this one?
You move the decimal 2 times to the right, and then you get 3,028.
There we go. So we're going from deca to deci, which is 2 jumps to the right. Do the same with our decimal. Good job. So that's going to be that. I promise this is a 3. There we go. 3,028. 2 moves to the right. Awesome. Now we just got 4 more. Let's go ahead and knock them out real quick. 7.1, and now I'm going to tell you, it doesn't matter which one you change, you're going to have to change one of the base units here. All right, because we've got meters on one side and liters on another. They're not going to equal. All right, so I'm just going to change this to meters. All right, so centimeter. 7.1 centimeters is equal to how many decameters?
I think it's 0.0071 decameters.
All right, so we're going to be moving from centi to deca. So that's going to be 1, 2, 3 jumps to the left, and that means adding 2 zeros in front of the number. So 0.0071 decameters. All right, so that is our answer there. Now let's look at number 6, 22 hectometers to centimeters. Zoom in a little bit for this one. Who's got it? Anybody got this one?
It's 220,000.
There it goes, 220,000. So we're starting with hecto. We're moving to centi. We're going to move 1, 2, 3, 4 times to the right, which means adding 4 zeros to that 22. So I'm going to go 2, 2, 0, 0, 0, 0, which gives us 220,000 centimeters. All righty. Now number 7, 1.3 grams to centigrams.
130.
130. So we're moving from base to centi, which is 2 jumps. So 2 jumps for the decimal gives us 1 more 0, and it's going to be 1, 3, 0. All righty. Now let's look at 88.21 decimeters to meters.
It's 8.821.
There we go. So we're going from deci to base, which is 1 jump to the left. So we'll move our decimal 1 to the left. So 8.821. There we go. All right, and look at that. We are done with our conversions. Good job, guys. We knocked that out real quick, pretty quick. Right here, let's get these definitions. We'll do these real quick right here, and then we'll get back to scientific theory, scientific method. So what's precision? What is precision? Let's get a definition.
Precision is a measure of the degree to which the measurements made in the same way agree with each other.
There we go. So the quick version is it's how closely your data agrees, or how close your data comes out to be. So when you're going for precision, that is grouping of results. So if we're talking sports, it's hitting the same place over and over again, hitting that same target constantly. But for hitting the same part of the target. But when we're talking about science, it's how closely grouped your data is. Alrighty. And the way to ensure that you do that is to do your experiment the same way over and over again. That's why there's the note and how closely they are, or how much they agree with each other. Now we're talking about accuracy. What is our definition for accuracy?
It's the degree to which the experimental value agrees with the true or accepted value.
There we go. So this is how accurate your answer is compared to what you are trying to get, your true or accepted value, your target, your goal. How close to the goal are you? If you're close, you're accurate. If you're not close, you're not accurate. Remember that you can be any of those 4 combinations of precision and accuracy. You can either be neither precise nor accurate and you're just bad at science, or you're not paying attention. You can be precise but not accurate, which is tightly grouped but off the goal. You can be accurate but not precise, which is where you're on the goal on average, but the grouping is not at all close. And then you can be both precise and accurate, which is where you get a tight grouping right on target, which is what you're aiming for. Alrighty, then the last math right here, because we'll have a little bit of density after we get to the scientific method. Let's go ahead and look at this. I'm going to zoom in some so I can actually write on it. I'm gonna, just like last time, I'm going to do a couple, you're going to do a couple, alrighty? So the first one we've got, we're moving from decimal notation to scientific notation. So that means that I'm going to have to figure out what my coefficient is. I'm going to remind you that you should have some form of this right here, where C is somewhere between 1 and 10, and N is a whole number, whether positive or negative. All right, so your first goal when you see a number that is larger than 1, or excuse me, larger than 10 or less than 1, you're going to have to figure out what your coefficient is going to be. So that means you're going to have to find the first non-zero digit and generally put a decimal after it. All right, so if that's the case, our coefficient here is going to be 5.602. So 5.602 meets that requirement of being between 1 and 10. And then here comes the slightly difficult part. You have to figure out what your exponent is. The way I like to think about this is if my new coefficient has a decimal point right there, it would show up right there in that number. How many jumps and in what direction do I have to go to get from my coefficient to my original number? So this can be 1, 2 jumps, and I move to the right. So this exponent needs to be a positive 2. All right, if I'm moving to the right and getting larger, our exponent is going to be positive, and however many times I'm moving gives me the number. If I am going to be getting smaller, if that's the case and the decimal moves to the left, my exponent needs to be negative. All right, so let's look at number 2. Number 2 has 2.3 times 10 to the 6th. So this positive 6 tells me I'm going to be moving my decimal to the right that many times. So I'm going to have 2. All right, then this is going to be 1, 2, 3, 4, 5, 6, and a decimal right there. So if I were to draw that in, that is 2,300,000. All right, now I'll do this third one, and then we'll let you guys help me out. I've got 5.5 times 10 to the negative 2. This negative 2 tells me the decimal moves to the left 2 times. So that's going to be 1, 0, and then a 5, 5. All right, so I move my decimal to the left 2 times to get this right here. So, who wants to handle number 4? Who wants to help me put that into scientific notation? First, what's going to be my coefficient?
2.27.
There we go. So that is solidly between 1 and 10. Now, what's my exponent going to be? How many times I'm going to have to move that decimal, and in what direction?
5 to the right.
All right, 5 to the right. That means it's going to be times 10 to the positive 5. There we go. All right, let's look at number 5. What's my exponent, or excuse me, what's my coefficient going to be?
9.1.
9.1. There we go. Between 1 and 10, 9.1. Now, what's my exponent going to be? What is it going to be? Go ahead.
-5.
Negative 5. All right. So 1, 2, 3, 4. This is actually going to be a negative 4 here. So you would move the decimal 4 times to the left in order to get this original number. So the way I'm going to suggest you do it is once you find your coefficient, put a decimal where that decimal shows up, and then just count 1, 2, 3, 4 jumps, and then to the left, which gives us a negative 4 as our exponent. Alrighty. Now let's look at number 6. What direction am I moving the decimal and how many times?
To the right 3.
To the right 3 times, which means adding 2 zeros. All right, so it's going to be 9300. So that's going to be 9,300. And then last but not least, this time literally not least,
0.0335.
there we go, 0.0335. So I'm going to move that decimal to the left 2 times because of this -2. Hopefully this now makes sense. If it didn't, or at least reinforced and had you kind of practicing in your head what we were supposed to know from this. And then now we're going to switch gears and head up to the, back here. We're going to head up here to these questions, and we're going to talk about that scientific method stuff just to make sure you can read a paragraph like that and then pick apart what you need to know. All right, so if you give me just a second, I'm going to erase these really quickly. So far, do we have any questions about what we've gone over? We've gone over the metric system, unit conversions, all that good stuff. Does that bring up any questions? Hopefully you guys are feeling pretty confident about this test, especially since we've had plenty of time to fill that out and you know, get through it together. Hopefully you are more than amply prepared for what we're going to be doing on your test day for you all. That is Thursday. All right, so like I said, we're going to be reading these paragraphs. I'm going to read the paragraph to you, and then we're going to answer those questions. So you won't see a question quite like this on the test, but it is really, really good practice to have a different way of thinking about something that you will be tested on, even if it's not the same way you'll be tested on it. All right, and these questions here really make you go back and refer to a thing here within the paragraph. So the very first paragraph states, an experiment was designed to investigate the effect of caffeine on the heartbeat of water fleas. 2 populations of water fleas were grown. Both populations had water with the same mineral content, were supplied with identical amounts of food, and received the same amount of light and had their temperature maintained at 20 degrees Celsius. Every 2 hours, water fleas from both populations were selected and their heartbeats were monitored. The flea of the population 1 had caffeine the fleas of population 1 had caffeine administered 5 minutes before their heartbeat was checked. The fleas of population 2 were given nothing. After the experiment, fleas that had been administered caffeine had a heart rate of 58 beats per minute on average, while fleas that had not been administered caffeine had a heart rate of 46 beats per minute on average. Now I'd ask you some questions about that. All right, so I'm going to highlight, and that'll help me identify some stuff as it asks. What part of the experiment was the caffeine? All right, so one group got caffeine and another group didn't. And the experiment was designed to investigate the effect of caffeine on heartbeat. Why is that a mark through? It needs to be a highlighter. So let me undo that. So, what you got? What is it supposed to be if it was designed to investigate the heartbeat, the effect of heartbeat?
The independent variable.
This is going to be our independent variable. This is what you are changing. So some of the fleas got this treatment. They actually got caffeine, and you wanted to see whether it affected their heartbeat. So successfully determined whether or not it affected it. So that's going to be your independent variable. Now let's look at number 2. What part of the experiment was the water temperature? So I want to then highlight this in blue. So both populations. And then had their maintained at 20 degrees Celsius. So both populations had their temperature maintained at 20 degrees Celsius. So what would that water temperature be?
Constant.
This is a constant. This is to make sure that it wasn't that the fact that their water was too warm. So just be aware that this right here is, I know you might have been like, well, where does it say water temperature there? These are water fleas. They live in water. So the temperature is the water temperature. So this is going to be our constants here. You're holding this constant. All right, now what part of the experiment was the heartbeat?
The dependent variable.
There we go. So I want you to notice, let me do this right here. Right here, we have heartbeat rate of 58 and heartbeat rate of 46 beats per minute. So we measured these at the end, and so that's going to be our dependent variable. All right, now what part of the experiment was the control group? So who was their control group?
Population 2.
There we go. Fleas of population 2 were given nothing. And then what part of the experiment was the experimental group? Which group were you experimenting on?
The first population.
There we go. Fleas of population 1 had caffeine administered. There we go. So this right here told you everything you need to know, and it became pretty easy. I'm just going to start erasing these. So hopefully that made sense, and you can start to see how experiments are set up. So you wonder, does it affect their heartbeat? Well, how am I going to test that? Well, I need to keep everything else constant, but then I'm going to administer that caffeine, and we're going to see just how that affects it, and we're going to measure that. All right. This is a pretty good experiment. Now let's look at some turtles. I love turtles. All right, so an experiment was designed to investigate the effect of steroid use on the speed of land turtles, trying to make them beat that hair finally, right? So 2 populations with 10 turtles in each population were selected. Both populations had food with the same nutritional content, the same access to water, and exposure to the same temperature, weather, and sunlight conditions. The turtles were kept in these populations for a month before the test, just to get them acclimated to that area. Population 1 had a topical steroid cream applied to their shells daily at 9 a.m. throughout that month, while population 2 went steroid-free for that month period. After a month, the 20 turtles were raced on a 20-meter track, and times were taken and speed was calculated. Average speeds of the 10 turtles without steroid cream were 0.27 meters per second, whereas 10 turtles that were administered steroid cream were 0.26 meters per second. What part of the experiment was the 1 month prior to the race?
Constant.
All right, so that's going to be a constant. So the 2 populations right here, the same, all of that, everything was being kept there for a month. Everything was constant there. All righty, now we're looking at number 2. What part of the experiment was the speed of the turtles?
The dependent variable.
This is going to be our dependent variable. So we've got this right here and this right here. This is what we were measuring. So we measured that. That's going to be dependent on whether or not it had steroids. Then I'd ask, what part of the experiment was the topical steroid?
The independent variable.
The independent variable. All righty, so we've got had steroid cream applied to their shells. So that is the independent variable. Now, what part of the experiment was the control group?
Population 2.
There we go. Population 2 was steroid free. There we go. What part of the experiment was the experimental group?
Population 1.
So population 1, why? Okay, whatever. Population 1 is our experimental group. Now, what would your conclusion about this experiment be? So this is not necessarily, find something in this. It's after you read it, what do you think the conclusion for this experiment would be?
The steroids didn't really help that
Okay.
much.
They didn't help much. Do you think they hurt?
Maybe, but I mean, I don't really have enough evidence to decide on that.
Okay, so the only evidence you're able to go on is what they've shared with you, which is why the more data, the better when communicating. And it says that the ones without steroids went 0.27 meters per second. If you did not realize, that is 27 centimeters per second. All right, that is approximately 10 inches per second. And the other ones went 26 centimeters per second. Is that is that a definite difference? Is that a really big difference?
No.
No, and I want to remind you, just like humans, turtles aren't all the same. They might have had some athletic turtles, they might have had some lazy turtles, they might have had some middle of the road turtles. And there's no guarantee, like how does the turtle know that it's racing? Right? It's moving down a track, but what if it stops to eat something? What if it stops to check something out? What's making it go forward? And so you kind of find that they really don't have a way to determine whether this was useful. And also, why do you think, like, if the steroids might have helped? They didn't, but if they could have, why do you think they didn't? Where did they put the steroids?
On their shelves.
All right, so if you wanted to do a topical ointment, maybe like Neosporin, or maybe you're trying to like spruce up your skin, you want to rub in some moisturizer, would you put it on your fingernails?
No.
Their shells are made of the same thing your fingernails are made of, but they are about somewhere like 20 times as thick.
Or order Subway. We ate foot-long subs all the time.
Let's go ahead and get that mic muted for me. As much as I'd love to think about Subway. All right, so the idea here being that it looks like the steroids weren't helpful at all. And, technically, just based on the data, it hurt them a little bit. But that I would argue was just random variation in individual turtles. You can't really say one turtle is, you don't know what to expect going into that. So pretty confidently say that it didn't help, though. So that would be your conclusion. All right. So I'm going to pause the recording, and we're going to pick up once we get to the density stuff, which will be in just a second. So now we have moved on to the density review. And with this density review, we're going to practice a couple problems, and then I'll write one in while kind of explaining it. I'm just going to give you the knowns, the way this is set up. If you notice, it asked for each of the two knowns, which of the three variables we're discussing here are unknown, and then you're going to have to do a little bit of math. I'm going to give myself some room to work here. So the first problem states that, or it asks, what mass of water in grams will fill a tank 100 centimeters long, 50 centimeters wide, and 30 centimeters high? Now, this triangle answer here, I'm going to remind you that triangle can potentially save your life here. All right, so we've got this triangle, and I'm going to decrease my font size just a little bit. We've got mass up top, density and volume down bottom. Again, it doesn't necessarily matter which one goes where in the bottom. It just matters that density and volume are down there because multiplication is communicative. So it doesn't matter what order you multiply. So we've got this triangle right there, and that means that, oh, that is not one solid thing. Let me just move. Can I just move all of that? Oh, awesome. So we've got this right here, and let's determine what we know. So what is given is you've been given volume, and you know that the volume is 100 by 50 by 30. Okay, so this lets me know that I've got 3 centimeters measurement, and this is going to give me a cubic centimeter answer. So this will give me my volume. All right, and if that's the case, 100 times 50 will be, anybody know? 100 times 10 is 1,000. 1,000 times 5 is 5,000. So 5,000 times 30 will be 150,000. All right, does that make sense? So we've got 5,000. 5,000 times 3 will be 15,000. And then add that 0 and it becomes 150,000. So we've got 150,000 cubic centimeters right there. That's one of our nodes. So we've got a volume of 150,000 cubic centimeters, or, you know, actually, let me not do a slash. Or milliliters. They're the same thing. So we know that. Does anyone remember what the density of water is?
It's 1.
It's 1. So that's going to be 1 gram per centimeter cubed or per milliliter. Okay, so we've got 1 and then that, and then now we're looking for the mass. So mass, based on my triangle here, mass is equal to density times volume. So what's 1 times 150,000? Anybody?
$150,000.
There we go. So we've got 150,000. Now what's our unit here?
Grams.
Grams. So this is going to be grams. It's asking for a mass, which is our, that's going to be our key, and it says in grams. But just to remind you, when you multiply density, so let me just show you the units, grams over centimeters, oop, that's a C, I promise, centimeters cubed, and then you multiply this by centimeters cubed, these cancel, and you're left with nothing but grams. So just as a reminder, anytime you multiply density and volume, the volume measurements cancel, and you're left with grams, which is why you get a mass answer. All righty. So let's get that mic muted, please, unless you got a question. And now we're looking at number 7. So number 7 says that a graduated cylinder is filled with water to a level of 40 milliliters. This is looking like volume 1, okay? When a piece of copper is lowered into the cylinder, the water level rises. This is volume 2. It rises to 63.4 milliliters. It wants you to find the volume of the copper sample. Okay, so you're going to have to find the volume based on this. Then it says if it has a density of 8.9 grams per centimeter cubed, remember that milliliters and centimeters cubed are the same. It wants to know what the answer in mass is going to be. So again, you've got your triangle of mass over density times volume. and it's asking for mass again. So you're going to have that same equation of mass is equal to density times volume. Now you're going to have to calculate here what your volume is. And so this is displacement. And remember that volume of the object that you drop in the water is equal to V2 minus V1. So you're going to have to subtract this 40 from 63.4. Hopefully you can do that in your head. If 60 is 20 more, and then you got 3.4, that means that our volume of our object is 23.4. And I'm going to go ahead and make it centimeters cubed so that my answers match centimeters cubed. So that's one of my knowns. So I'm going to write that right here. So that's going to go right there. It's also stated that it has a density of 8.9 grams per centimeter cubed. So, what's up? What are we going to do? How are we going to solve this?
You're gonna multiply the density by the volume.
There we go. We're going to multiply density by volume. So that's going to be 23.4 multiplied by 8.9. And that's going to give us, I'm going to write that down. Let me go ahead and extend that page. So 23.4 centimeters cubed multiplied, make that parentheses, 8.9 grams per centimeters cubed. All right, so centimeters cubed cancel. I'm going to be left with an answer in grams. And this comes out to be 208.26, and my answer's in grams. So you've got a 208 gram sample of copper that rose the water level by 23.4 centimeters cubed or milliliters with a density of 8.9 grams per centimeter cubed. So I told you I'm going to give you one more. I'm going to give you some knowns and then ask for an unknown. All right, you're going to have a mass equal to 26 grams. I'm going to give you a density of 9.2 grams per milliliter. And I want you to find the volume. All right, remember the triangle. If you're solving for a number, you cover it up and then use the operation of what's left over. So I'm going to give you about 3 or 4 minutes to work on that. Couple more minutes. All right, now we're back. Hopefully you had time to work on that. So anybody want to tackle that? What is volume equal to? Anybody? All right, well, I'll take it. Volume is equal to mass over density. If we look at our triangle, you cover up the volume, you see mass is over density. So if I'm going to do that, I'm going to plug those values in of 26 grams over 9.2 grams per milliliter. And the grams cancel. Cancel that gram. And then 26 over 9.2 is going to give me 2.8, and I'll say 3 because it rounds up. 2.83. And then what's my unit here? You're right. It's the milliliter. All right, so 2.83 milliliters. And so we've done enough calculating density to know it's mass over volume to where I just wanted you to see calculating out mass and then calculating volume, and also just noticing that you may have to calculate volume in a problem where you're either calculating density or mass, where you're given either displacement or measurements. So just be aware of that if that's the case. So do we have any questions before we get out of here? Pretty straightforward. All right, so I'm going to go ahead and